Okay, so we've seen before that Max Planck had suggested that light, which we know as a wave, has wave-like characteristics, can also exist or can exhibit particle-like characteristics. And Einstein showed that through the photoelectric effect. Now, what Louis de Broglie reasoned later on was that if light, which we know as a wave, can also exhibit a stream, can behave like a stream of particles, which Einstein said was photons, then de Broglie suggested that electrons, which we know are particles, okay, these are subatomic particles, maybe these could also exhibit wave-like characteristics or wave-like properties. Now, again, thinking about the wave-particle duality of light, it made sense that he suggested that electrons could also exhibit wave-like characteristics. Now, according to de Broglie, these electrons, instead of being like a propagating wave, like a wave in the ocean, these electrons would behave like standing waves. In other words, they kind of oscillate up and down. In the example that's shown here, an analogy to this is that if you pluck a string on a guitar, it vibrates up and down, right? That's a standing wave. And only certain wavelengths are going to be allowed when we have these standing waves. Now, if we take a look at an example of one such standing wave, okay, so on this screen, you can kind of see the string kind of oscillating up and down. It's a standing wave. It's not propagating from left to right, okay, across the screen, for example. It's not going like like a wave in the ocean, for instance, just going kind of up and down. That's what we call a standing wave. Okay, what you'll notice in the standing wave is that, yes, you have a peak and a trough and a peak and a trough, and it kind of oscillates between both of those along the wave. There are certain points along the wave, the standing wave, where it doesn't change, where the amplitude does not change, and these regions here in red, and those are places along the wave that we call nodes. Okay, and that's going to be important to keep track of that. Right? So at a node in a standing wave, the amplitude of that wave is actually zero. In other places, it kind of oscillates back and forth. So only certain wavelengths are allowed in order for this standing wave to exist. Now, de Broglie suggested that the particle and the wave properties of electrons, for example, or actually any particle, can be related by this equation. So we have lambda, okay, which we know already, that's the wavelength, is equal to h, okay, so that's Planck's constant, divided by the mass, m, and that mass has to be in kilograms. You'll see why in a second. And then u here is the velocity, okay, or the speed. Sometimes you'll just see v, okay, not nu, but v, right? And that's where it can get a little confusing, which is, I suspect, why they use u in this case. There are other reasons, but that's one of the benefits of using u rather than v. But it represents a velocity in either case, and that is in meters per second. So we can calculate the wavelength of a particle, for example, which seems kind of counterintuitive, but that wavelength that we calculate is known as the de Broglie wavelength, or de Broglie, however you want to pronounce it. So let's take a look at an example, and we'll take a look at the first one here. So let's calculate the de Broglie wavelength of the particle in the following two cases. We have a 25-gram bullet traveling at 612 meters per second. All right, so we're going to use the de Broglie wavelength. We need to use the de Broglie equation. So our wavelength here is equal to h, right? So we have Planck's constant. So that's 6.63. Well, let's back up the Planck's constant here for a second because it's important that we use the right units. Okay, so h is equal to 6.63 times 10 to the negative 34 joules times seconds. Now, if you recall up here in our initial foray into the de Broglie expression, okay, the mass here is in kilograms of the particle, and then we have meters per second. So what we need to do is to actually now relate the Planck's constant to a form that actually has kilograms in it. So if you recall from earlier on, the joule is the same as kilogram meters squared per second squared. Okay, so if we substitute that into where we see joules, this would be 6.63 times 10 to the negative 34. So joules now would be kilogram meter squared. I'm sorry, write that properly, kilogram meter squared per second squared. Okay, and now times the second, right, this part here. So what happens? The seconds cancel. So we end up with the units now of Planck's constant being 6.63 times 10 to the negative 34 kilogram meter squared per second. Okay, and we want to use that unit because we have kilograms in our mass, right? So we want to make sure that we use the correct unit. Now we're given the mass of the bullet in in grams. You want to convert to kilograms. Okay, you want to make sure that units are correct. So we have 25 grams. We just simply divide by 1,000. So we end up with 0.025. So we substitute our mass in here. Okay, we have our velocity that's given as 612 meters per second. So that's our U. And then we have our Planck's constant with the correct unit that goes in. So we substitute those in, and what we see is that our kilograms are going to cancel out. We see that the seconds are going to cancel out. We see one of the meters is going to cancel out down here, and we end up with meters as our unit. That makes sense because we're trying to find the length of a wave. And if you'll notice, okay, the length here is really, really tiny. So really small wavelength. And that should make sense, right? If you think about a bullet, it's fairly small to begin with, but it's actually really big compared to something like an electron, whose wavelength is a lot longer, right? -5 versus -35. That's, 10 to the 35 difference between the wavelength of the bullet rather than the wavelength of an electron. So because the wavelength is so small, you cannot see this with your eyes. So not observable. So if you see, videos of people firing bullets, you don't see the bullet kind of oscillating up and down, right, in a wave. That's impossible to see. The wavelength is way too small. In the case of electrons, though, which is what part B is, the wavelength is a lot smaller, right, 10 to the negative 5 meters, and that's something that can be calculated in this case. And again, a particle possessing wave-like characteristics. The other simple experiment that helped show that particles can also possess wave-like characteristics is this whole idea of diffraction, right? We saw diffraction before. So we say recall diffraction of light waves or just regular waves. We saw the diffraction pattern. If we do a similar experiment with electrons, we actually see something very, 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 very similar, right? Alternating light and dark images. We see that with X-ray diffraction patterns as well. So this also shows us then that even though we're dealing with electrons that are subatomic particles, experimentally, this is what we see by doing these experiments. So we can't really say that this is being made up because you actually see this. They possess this property of diffraction, which is a wave-like characteristic.